Once again, good morning, everyone. I would invite Deepa ma'am to start the session.
Good morning. So am I
Yes, ma'am, you are audible.
okay? So last class, so for the last two classes, we have been doing the periodic table, right? So the periodic table, we know what is a periodic table, what was the necessity of the periodic table. So we have been discussing this for a very long time. Even we know about the history of periodic table, why like nothing comes in one day, right? Everything has to come and everything has to be paid, right? So many of the scientists gave their own ideas. Many of the scientists, they used to believe like there can be different properties that can be used to just create a law. So create a periodic table. Okay, so that was the main idea. So different scientists proposed. So Davenius tried, who said that a group of three could be beneficial, but it was not applicable for all the elements, and thus it was rejected. Then came Newland's law of the octet in 1864. Then came the Lothermius atomic volumic curve, which came in 1869, and so on. So there then came the Mendeleev's periodic law, but it was an old concept. Why an old concept? Because he decided to play an important role by arranging the elements with respect to the atomic weight, which was obviously not possible for all the element, because once all the elements have been classified, then just wait for once. Once all the elements have been arranged, it was seen that all the elements could not be arranged according to their increasing atomic now weight. So this theory was again rejected. Okay, so this was the basic idea which gave us the idea for the periods, how many periods are there, what are groups, how groups are different from periods, and last class we discussed in details what is the 2818 18 and 32. We all discussed this. So this was an important thing. So we know about the old periodic law where lanthanides and actinides were given a separate position, but nowadays they are considered to be an F block elements. Okay, so from left to right in a period, generally the atomic weight, effective nuclear charge, ionization potential, electronegativity, electron affinity, all the things were generally increasing, and there are some properties which generally decreases. And I told you that if you are remembering these properties with respect to period, then obviously you don't have to remember for groups, because this characteristics of the periods, these are in reverse orientation in groups. So okay, so we also know about the diagonal relationship where second period and third period elements show this property. Lithium is similar to magnesium, beryllium with aluminium, boron with silicon. So the yeah, so these are like in diagonal relationship. So they are like diagonal to each other, and that is why they are in the diagonal relationship. So then we came to know about different groups. In the old groups, there was 1A, 1B. All the A's were the normal, B's were the transition elements. These two have been totally been separated while you are like talking about in the new periodic table. So there is no resemblance in the elements of the subgroup A and subgroup B of the same group except the valency. This we all know. And there were the transition elements, normal elements, and so on. So, okay, so this was the different thing. And then Moseley gave a law which actually gave the idea to arrange the elements on the basis of increasing atomic number and not the atomic weights. So this was the long form, and even Bohr at that time, if you have read the atomic model, that chapter, you know that Bohr proposed a atomic model where He tried to make people understand why elements vary. Why vary? Because they have different number of the valence electron, and since the number of valence electron varies, their capability of accepting and donating an electron also varies, and it is the capability of an element to donate or to accept an electron which is the sole determining property for any element's chemical properties. So Bohr was the first thing which made people understand this. So it is the atomic number that is actually responsible, because you think atomic number is related to the number of the electrons, not the atomic weight. Weight is something how much a particular atom is weighing. So if I know atoms can't be seen in your eyes, or even I can't see an atom, but atomic weight is something like you just take an atom and place it on a weighing scale and you measure the atom. So the number of electrons are playing no role in that. Okay, so maybe yes, obviously number of electrons do play a role, but it is not playing a direct role. But atomic number is greatly dependent on what? On the number of the electrons, right? So obviously arranging elements on the number of the increasing atomic number instead of increasing atomic weight is a far more better approach to classify the element. Is this part clear? Why the concept of arranging elements on increasing atomic number is more powerful than the increasing atomic weight? Okay. So this was the thing, and then we came to know about S block, P block, D block, F block. So we all know the basic characteristics for S, P, D, and F. Okay. So now, Bohr again classified the elements as the inert gases, representative elements, transition elements, inert transition elements, trans-uranium elements. We all know what are the inert gases. Inert gases, I told you, inert gases are the people with government jobs. Full stability, full life settled, best place in the periodic table, no one to annoy or to disturb them, right? So all the other elements, they decided to do and do like secretly sneak peek in the inert gases. So they all try to be the inert gases, and they all try to be the nearest inert gas. Okay, so many of you, last class I told you this thing. Wait. That lithium will try to be like helium, but sodium will try to be like neon. I told you, right? But you can ask me, ma'am, what about neon? So neon is also will neon 7 and here it is 10. So will neon accept 3 electrons or will lose 5 electrons? So neon can do both. They are just present in the middle. So sorry, it is not neon, it is nitrogen. So nitrogen, will it be try to be like neon or will it try to be like beryllium, or sorry, or will it try to be like hydrogen or someone else? So practically the stuffs which are right in the middle, they try to be like this. So we write the valency of nitrogen as +3, as -3, and so on, right? So that is the thing. So elements which are practically in the middle, especially you will see D block elements, they have a lot of valencies, +2, +3. Iron, where is iron located? It is 26, so iron is located here. So it has many valencies, +2, +3, right? So this is the basic concept. So they just all try to be stable. So anything they get, once they get the stable conformation somehow, okay, they are happy. Okay, and this is the mnemonic of what, where is the S, where is the P, where is the D, and where is the F. Okay, so these are the basic things we have already learned, and we discuss something about transuranium elements, what are transuranium elements, and so on. we know about the alkali elements, we know about the atomic radii. So what are the different types of the atomic radii? We all did in the last class. So there is a different formula for heteronuclear and there is a different formula for homodimer. Right. So accordingly, if you are reading biochemistry in future or any kind of chemistry, you need to find the distance between the two molecules there. Otherwise, you can use this formula. Okay. Next comes the crystal radii. It is defined as 1/2 of the distance between the nuclei of two adjacent metal atoms in the metallic close packed crystal lattice in which metal exhibits a coordination number of 12, right? So this is something I told you that it is exactly same like the atomic radii, but it is for a metal. Metals where coordination number is 12. What is coordination number? We will be discussing in the class 12 syllabus. But for now, we know that if it exhibits a coordination number of 12, and 1/2 of the distance, it is called a crystal radii. So R covalent, R crystal, R van der Waals. So atomic radii in a nth orbit is given by this formula. You know this formula. You have already read this in the first chapter, like in the atomic radii chapter. So you know this. N is the principal quantum number. I guess everyone knows what is a principal quantum number, what is a spin quantum number, what is azimuthal quantum number, and so on. Principal quantum number is the number of shell. Which shell you are talking about, that is the principal quantum number. A naught is the Bohr radius, Z naught is the effective nuclear charge. And this we discussed about the screening effect with a student, that you have exams nearby, you are sitting right at the center, and then your friend wants to come, but your house is now is being protected by your parents. So the force of attraction with you and your friend, it is being cut off. Why? Because of your parents will scream and threat your friend to leave that place, right? So there are many electrons present in the surrounding shell. Okay, so in the surrounding shell, many electrons are present. They are revolving, and in the center, there is the positively charged nucleus. Maybe that positively charged nucleus is attracting an outside electron, but the electrons of the valence shell, they are not attracting, they are repulsing. So the force of attraction is being reduced. So this is the screening effect or the shielding effect or the effective nuclear charge. And due to screening effect, the valence electron experiences less attraction towards nucleus. This brings down the nuclear charge, and the new nuclear charge, which is the decreased form of the original nuclear charge, we represent it by Z star. So it is related to the actual nuclear charge Z by the following formula. Z star is Z minus S, where S is the screening constant and Slater's rule for estimating effective nuclear charge Z star. So write about the electronic configuration of the element like this group. So we generally write in this formula 1s to 2s to 2p6, 3s to 3p6. Sometimes 4s comes before 3d. Hope you know this. Sometimes 4s comes before 3d in iron, I guess, because that has a different rule, but this is the Slater's rule. More Z star is reduced, so one Z star for 1s is less than the Z star for 2s. Z star for 2s is less than Z star for 2p. And thus, we write like this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4p, 4f, 5s, 5p, and so on. So we write like this generally. So now you do everyone know why for S we are writing 1s, 2, for everything we have S, but not for everything we have P. Like 2p is present, but for 2, 2d, 2f is not present. Why? You have already read the atomic radii chapter, right? I guess you know this. So, anyone come forward and explain it to me? Why there is 1s, 2s, 2p, but 3s, 3p, 3d, but there is no 2d? Why? Why is this happening? Anyone come forward and explain? Anyone? Do you guys know this? Have you been taught? This is just a basic concept. What is the azimuthal? Use that concept and just come forward and volunteer. No, this is not correct. Okay, let me explain this. So, if you're not understanding this, feel free to ask because you won't be able to solve questions otherwise. Okay, what is 1s, 2s? Okay, let's explain this. So, okay, what is 1s, 2s, 2p, 3s, 3p, 4s, 3d? All these things. This refers to what? This refers to orbitals of the electron in the atom, right? Okay, these all are the orbitals of the electrons, agreed or not? You know what is orbital at least. This is an electron. This is the nucleus surrounding are the orbitals. So 1s, 2s, 2p, we represent them. These are the representations of the different orbitals, right? So we are all, yeah, for the quantum number, but how? Okay, so let me explain this. So all this because of the quantum number, obviously, or it is of the quantum number. But what is these? 1s, 2s, 2p, these are the different shells. When we are in class 10, we came to know about K, L, M, N, and so on. We used to read like this, right? What is K, what is L, what is M, what is N, right? So KLMN are the different orbitals. But when we have grown up, we know K has different suborbitals. These are the now we have now grown up. We don't represent orbitals by KLM. Now we represent orbitals like 1s, 2s, 2p, 3s, 3p, and so on. Okay. So the reason you don't find orbitals like 2d or 3f, they are governed by the quantum numbers. So what is the principal quantum number? Principal quantum number is n. N for number. So principal quantum number is represented by small n. So this number actually determines the energy level or shell of the electron and can take any positive integer value. 1, 2, 3, etc. Okay. Azimuthal quantum number is L. This number defines the
So one, two, three.
yeah. So azimuthal quantum number is what? Azimuthal quantum number represents the subshell or type of orbital, like whether it will be S or P or D or F. And it is linked to the principal quantum number. L is equal to N minus 1. Is this part clear up to this? Everyone.
Yes, ma'am.
Why I'm not hearing an yes, ma'am, from everyone? Everyone I want to.
Yes, ma'am.
Okay, so good. So now we know L, just write in the copy, L is equal to N minus 1. Okay, suppose you are considering shell number 1. N is equal to 1. That is the first shell. Or when you were young, that was the K shell. So what you will see? N is equal to 1, L becomes 0. Right?
Yes, ma'am.
So when L is equal to 0, orbital is S only.
Yes, ma'am.
Okay. So,
Yes, ma'am.
okay. So suppose N is equal to 1. Then L can be 0. Only 0 L can be. Is there any other possible combinations? No. It can be only 0. So only a 1s orbital exists. 1p, 1d, nothing exists. 1 represent what? 1 is the n. N is equal to 1, and if n is equal to 1, L becomes 0. L becomes 0, it means only one orbital exists. So that is 1s. Okay, that is 1s. Is this part clear?
Yes, ma'am.
Okay, now n is equal to 2. What are the possible combinations for L?
Is equals to 1.
If n is equal to 2, so 2 minus 1, 1. Okay, so we are saying 1, but 0 has a value. Okay, so if n is equal to 2, L is equal to 1, and I told you consider 0. Okay, so 0 and 1. 0 means 2s, 1 means 2p. So is there any other possible combinations?
No, ma'am.
No. Good. If n equal to 3, L becomes 2. 2 means 0 means 3s, 1 means 3p, then 3d and so on. Is this part clear? Why you can't find 1p, 1d? Is this part clear?
Yes, ma'am.
Okay. So Slater's rule states that Z prime, we say that as Z star or Z prime. Z star can be calculated by 1s, 2s, 2p, 3s, 3p, and we are just arranging it in the increasing order. So 1s has this, 1s has less energy than 2s. So from lowest to highest, the electrons will be filled up. Now you will be learning the exceptions in the further details. So electrons in any group higher in the sequence that the electron under consideration contributes nothing to the shielding sigma. So what does this statement mean? So we already know about what is the explanation. Yeah. So what does this mean? Electrons in any higher group, higher in the sequence, that the electron under consideration contribute nothing to the shielding sigma. Okay, so this slide is about what? This slide is about Slater's rule. Why? Why we are learning Slater's rule? We are learning Slater's rule for estimating Z star. Slater's rule is actually a method which is used to approximate the effective nuclear charge, okay, which is experienced by any kind of electron. So Z effective is what? Z effective is the net positive charge which is felt by an electron taking into account the shielding effect of other electrons. Means how much attraction is left for the from the nucleus in spite of all the problems. Like you are present, you are roaming around the house of your friend. Still, how much willingness you have to enter that house to meet your friend, in spite of all the rebukes by his or her parents. I'm saying that only. Okay. Uh, just imagine this is a nucleus, okay? We all know there are different shells surrounding the nucleus. Preeti, is that clear? There are different shells surrounding the nucleus. Is this part clear? Okay.
Yes, ma'am.
Now you are a foreigner. Suppose you are here. Okay. Now your friend is in the nucleus, and his mom, dad, elder brother, all the neighbors are the electrons which are revolving around the nucleus. You are here. They all are standing with a stick that if they see you, they will beat you. Okay. Still, how much willingness is left inside you to overcome all these threats, rebukes, to enter this house? That is the effective charge. Obviously, if there were no problems, no electrons revolving, then the attraction would be very strong, right? You could have simply entered his house or her house, whoever your friend is, and you could have a good time. But since her parents are present, so it is creating a kind of resistance, I will say. So now your willingness has decreased. So that your willingness has decreased, that is the Z star. And previously, when there was nothing, no problem, that is the Z. So what is the difference between Z star and F? Z star is Z minus S. What is this S? How much repulsion is being provided by her parents? S is the screening constant. Is this part clear now?
Ma'am,
Yeah.
thank you.
Say. Okay. I hope this part is clear. Don't mix up this S with this S. Wait, my laptop hanged. Just wait for once. Yeah, don't mix up this S with this S. This S is for azimuthal quantum number. This S is for Slater's rule. No. Okay, so these are two different things. I told you this S is screening constant. To calculate this S, Slater's rule is applied. And after which you don't need to know, it is not a part of your syllabus. Your syllabus just tells you that Slater was a human, Slater was a scientist, or whoever he was. Slater proposed something to calculate this S. And after that formula, after calculation, he found this is the order. And that is why we generally feel electrons in this order. Is this part clear now?
Yes, ma'am.
Okay. So electrons in any group which is higher in the sequence than the electron under consideration contribute nothing to the shielding sigma. Means that electrons in the outer shell do not shield electrons in the inner shell. You may think that suppose, okay, this is not working. Okay, you may think that suppose this is the nucleus. Sorry, suppose this is the nucleus. Okay, just follow my laser point. Suppose this is the nucleus. Okay, can you see the red point like a pimple? Okay.
Yes, ma'am.
This is one orbital. Surrounding it is another orbital. Surrounding it is another orbital, and you are here. Obviously, you are facing a repulsion that is normal. But electrons present in the first shell, is comparatively more near to the nucleus as the electrons present in the outermost shell, right or wrong?
Yes, ma'am.
So the electrons which are present in the innermost shell, they will be more attracted to nucleus because for them no repulsion is present, right? Outer shell electrons can't provide a resistance for inner shell electrons. Is this part clear? Is this part clear?
Yes, ma'am.
Okay. If this is the part which is very much clear to you, then can I move on to the next slide? Yes or no?
Yes, ma'am.
Okay. So,
Ma'am,
yeah.
once repeat that last point, ma'am, that you
Okay.
said,
So
right?
this is the nucleus. See, this is the nucleus where the red point is. Okay. Now, surrounding the nucleus, this is one shell, this is second shell, this is third shell, this is fourth shell. Now you are here. This electron looking like a pimple at the right bottom of the screen. Obviously, this is facing the electronic repulsion, that is the Z star, we all know. Now, I told you what, this is the nucleus, surrounding it is the first shell, second shell, third shell. Right or wrong? Now for
Yes,
the first shell, we can say, for the first shell, we can say that the, what I will say, that shell, whatever electrons are present in the first shell, okay, that is facing more attraction towards nucleus. However, electrons are present in the second shell, they are being repelled by the first shell, right or wrong?
yes, ma'am.
Did you understand? I said this is the nucleus, this is one shell, this is two shell, this is the third shell. Okay, surrounding the nucleus, consider there are three shells. Innermost is the first shell, outermost is the third shell. Innermost shell has electrons. They are very close to nucleus. Is there anyone to stop those electrons from entering the house?
No, ma'am.
Electrons present in the second shell, they are being shielded by electrons present in the first shell?
Yes, ma'am.
Yeah. So just imagine, innermost shell has your parents. Second shell has your siblings. Third shell has the neighbors. Okay. So neighbors are least expected to enter the house during exam. And you are totally an outsider. So you are definitely allowed by no one. Parents don't need permission, right? So parents can enter the house, can beat the child, can rebuke the child, can love the child, can motivate the child, can do whatever with the child. Siblings can, because parents will say she's studying or he's studying, why are you disturbing? So just imagine like this. Okay. So this point means that always the electrons present in the innermost shell, they will shield the outermost shell electrons. Like the innermost shell electrons, they are shielding the second shell electrons. No, you can't feel so much attraction towards nucleus. And second shell electron and the first shell electron, they together are providing a resistance for the third shell electron, right? No, you can't enter the house. And all the shells, cumulatively, they are providing resistance for you. No, you are a total outsider. Obviously, you can't enter the house. Now, Still, if you have the willingness inside you to enter the house, that is the Z star. And so Z star is what? Original Z, which you original willingness of you to enter the house minus the resistance created by all the three levels. Okay, so is this part clear? So to calculate how much resistance is being provided by the students, Slater was a human who calculated, who gave some formula, and using that formula, we know this. This is the ultimate rule. 1s, 2s, 2p, 3s, 3p, 4, 3d, 4s, 4p, and this is. So is this part clear now?
Yes, ma'am.
Any doubts, anything? Just read this slide once now and then tell me. And I am asking you one more question. For iron, you can see 1s, 2s, 2p, 3s, 3p, then 4s, then 3d. Why this happens? You should have known this from the first chapter, that atomic radii chapter. Before this chapter, you read about some chapter. Now you answer me this question. This is the Slater's rule. So obviously, why for some elements we write 4s before 3d?
Kunst rule, ma'am.
Yeah, so you have to explain it. Just take a minute and then explain. So, can anyone tell me what is the principle that we follow? For stability is okay, but what is the name of that principle? Aufbau principle. N plus L rule. Yeah. So that is the N plus L rule. So hopefully everyone knows the N plus L rule. Then I won't explain it again.
Yes, ma'am.
Okay. So I'm not explaining it again. So that is the N plus L rule. This is the original configuration. But after Slater came Aufbau. And then he said, no, this will be an N plus L rule. And then he gave that concept. Okay. So just wait for once. So then for an electron in NS or NP orbital, all other electrons in NS or contribute to sigma 0.35 each. All electrons in N-1 electron contributes 0.85 each. This contributes 1 each. And for an electron in an NF or ND or NF orbital, all electrons in the same group contributes 0.35 each. Those in group lying lower in the sequence, they will contribute to 1 each. Radius is also dependent on the extent of the force of attraction, which pulls out the external shell inward. So this is just saying how to use the Slater rule. Nobody will ask you what is contributing what. So just for your understanding, I am just saying C. NS or NP orbital. Then all the other electrons, for an electron in all other electron, NS, NP orbital contributes atto. Then for N-1, that is more higher, they contribute 0.85. See, the repulsion is higher. Whatever I taught you, more you go up, more the repulsion will be increasing. Okay, more you come close, it is like almost 0.35. And above it is, this is you. This is the attraction faced by you. Okay, so this is the basic concept. Nobody will ask you. If you can remember the value, very good. If you can't remember the value, don't have to mark up. Okay, so radius is also dependent. Obviously, all the electrons don't have, or not electrons, all the atoms, they don't have same kind of radius. Some can be fat, like atoms are like just like humans. Some can be fat, some can be skinny, some can be with a good figure like a model, like perfect. Okay, so atoms are also like humans. They are of different shapes and sizes. So for a fat atom, so radius will be quite high. So for a normal atom, like a model atom whose figure is quite good, like perfect, maybe that atom goes to gym to maintain his or her figure, that atom has an extent value of standard value. But there may be atoms who are quite skinny in nature, so obviously their radius will be less as compared to other things. So but this rule will remain constant. Present in the innermost, nobody is applying a resistance. More outermost, more you are facing the resistance, and that value is also being given. So is this part clear? So if just try and solve each and every question regarding to whatever I have taught up to this. There, variations in the period. See, this is just a variation in the period. Z, this is the Z star. And nobody asked you to remember this. This is just an explanation, like lithium, beryllium, boron, carbon, nitrogen. This is like a group, and this is how it varies along the period. Okay. So this is just for a chart to remember in a period left to right. Z is the atomic number, increases by 1 unit, like this. Z 3, 4, 5, 6. See, everything is Z is the atomic number. It is increasing by 1 unit. Okay, Z star increases by 0.65 unit. Okay, again see. Z star 0.65 unit. Okay. If you can remember one, you can be able to remember everything. Then you don't have to mark up also. This is the beauty. Then that is the reason I wrote in the PPT like this. N is the number of shell which remains constant. Always remember, in a period left to right, this remains constant. N always remains constant. See. Okay, 2, 2, 2, 2, 2. N is the what? Number of shell. Everyone has 2 shell. This always remains constant. That is the reason this chart is something I have taken from the book only. Just copy paste it. And thus Rn, the formula for Rn is 1 by Z star. Just calculate it for 1 by Z star. Now there is an exception. What is the exception? In case of noble gases, like in neon, there is no covalent bond formation. Remember, this neon has no covalent bond formation. Hence, only van der Waals radius is considered. Thus, there is high jump in the value of radius from this to this. This is an exception you have to remember, because people like exceptions. They will be asking you for the exceptions. Okay. So for each and every trend, I am to suppose we have read about screening effect. I will show you a chart if that chart is important. Then what is increasing, how much is increasing, then the number remaining constant. Then we can see a formula, if there is any formula or not, which is any famous formula, and there is any exception. For this is the basic, template that we are going to follow. Is this part clear? Is this thing becoming easy for you for a periodic table? Because if you start reading each and every characteristics and the whole periodic table, you can't remember everything. Understand the logic, then conclude certain points, then just memorize this slide. Not this slide, the chart which I have showed. Then memorize the chart. Then in exam, whichever element they ask you, They will not be asking you about an element which has not yet been discovered. It is not possible for them. So you practically have remembered each and everything of the periodic table. So periodic table automatically will become your strength. Okay. So is this part clear till now?
Yes,
Whatever,
ma'am.
however we are starting, however we are reading, in case you have problem with this kind of template, you can tell me. We can learn from different templates also. Next, variation in group. We read about periods. Now we will be learning about group. Now you will be understanding nothing. So in a group means top to bottom. I am writing in a period right to left to right. In a group top to bottom. Maybe in the future notes, I will not be writing this. I'm writing this. Why? Because you are a naive. You are just a kid, newborn kid. So maybe you get confused what is group, what is period. Then you will start finding in your book. Then you will get totally distracted. What you are reading. So in a group, Z increases. See, in a period, Z will be decreasing. Oh, sorry, Z is increasing, but in a period, Z was actually increasing by 1 unit. And here also, see, Z 3, 11, 19, 37, 55, 87. There is no possible, what I will say, mnemonic I could find to remember 3, 11, 19. But in a period, I saw that the Z was increasing by 1 unit. So I wrote. But here you have to memorize this, that Z is increasing. But but it is increasing randomly, more basically. 3, 11, then 19, 37, 55, 87. It has following no pattern. So Z star almost remains constant. See, Z star is here. So see, except for this, everything is constant. So you just need to remember this value. Other values remain constant. Okay. So N increases, N obviously will have to increase. 2, 3, 4, 5. N increases serially. Okay, so I have not written N is increasing serially. But in the period, N was remaining constant. Number of shells. Always remember this. Okay, so N is increasing and what? Radius. And atomic radius in a group is dependent on the value of N. We all know. I just told you that there may be a skinny atom, there may be a model atom, there may be a fat atom, and it just depends. So Rn is n square by z star. So if you remember these values, obviously you can calculate it sitting right in the examination hall. And if they ask you about the atomic radius of this is greater than this and followed by 4 statements, you can calculate. Next comes ionic radii. Is there any something you need to know about atomic ionic radii? Because once you know about those chart, you already have memorized, but you now need to know the logic behind it. Okay, so what is ionic radii? It is defined as the distance between nucleus and the outermost shell. Okay, or its distance between the nucleus and the point where the nucleus exerts its influence on the electron cloud. Actually, nucleus will always provide an force of attraction. Power of the nucleus is like seductive in nature. It will just attract everyone in the environment. So up to which it can show its attractive nature from the nucleus, center of the nucleus up to that point. You have to consider that is the ionic radii. So distance between nucleus and the outermost shell of an ion in most cases, or distance between the nucleus and the point where the nucleus exerts its influence on the electron cloud. Okay? Any confusion, anything you can't imagine here from here? Is there anything you can't understand from this definition? speak up? Anything. Yeah, someone wrote in the chat box. Atomic radius. This is ionic. That was the atom. You are considering the whole atom. Here you are just considering the nucleus and the outermost shell. Okay. Atomic was what? There were two atoms. If these two atoms are similar, we are using one formula. If these two atoms are different, we will be using another formulas. Okay. That is the atomic radius. Ionic radius is we have one atom. We are considering only that. Center of the nucleus to the outermost shell. And that is the atomic radii. Two atoms, similar type. Two atoms, nearly similar type. Two atoms, completely different type. Three different formulas we got. Is this part clear? Someone who asked me. Ayushi. Is this now clear? What is the atomic radius? What is the ionic radius? Is this part clear? Just say it loud. Okay. So metal ions are smaller than the atoms from which they are formed. These are fact-based slide. When a positive ion is formed, number of the positive charges on the nucleus exceeds the number of orbital electrons, and the effective nuclear charge is increased. Who can volunteer me to explain? This results in the remaining electron being more strongly attracted by the nucleus. These electrons are pulled in, further reducing the size. This is the statement. This is the explanation. Now, who will explain me? Who is going to volunteer to explain this? Volunteer to explain it? See, it is trying to say why. So it is just trying to say why the metal ions. Yeah, ma'am. Okay. So it is just trying to say why metal ions are smaller than the atoms from which they are formed. Okay, why? When a metal atom loses electron to become a positive ion, it is called a cation. Okay. Everyone agrees with this?
Yeah, ma'am.
So the number of positive charges on the nucleus compared to the number of the electrons, this will increase because it has become positive as a whole. True or not? Now, as the cation loses electron, effective nuclear charge increases. Means the remaining electrons are being pulled more tightly. More tightly means what? Squeezing. So the ion becomes more smaller. So what I can say, loss of electron in metal ions lead to a stronger nuclear pull on the remaining electrons, resulting in smaller sizes. Okay, see, all you know, number of electrons and number of the protons are equal. You read in class 10. Yeah, you read. Yes or no?
Yes, ma'am.
Okay, now there is a metal. Okay, metal has a tendency to lose electron. And I told you, once someone loses something, they becomes positive charged. Just imagine, like electrons are like currency. Okay, if you lend your friend some money, then people will think, oh, okay, he or she is a great donor, so your respect will become positive. Okay, and if you are snatching money or taking money from someone, people will think, oh, she's poor, he's poor, he has to borrow money, so your respect becomes negative. Okay, so think like this. Okay, so metal ions, they are actually rich people, they are Ambanis. Okay, so Ambanis that donate, so they have a tendency to donate, so that is the reason they donate, and after donating, they their respect respect increases means positive. Okay, now we know, for any ion in nature, metal, non-metal, whatever you are going to discover being a scientist in future, all has number of protons and number of electrons, which are exactly same in nature, same in number. Like number of protons is equal to number of electrons. Okay. For metals, this is the case. I told you metals have a tendency to give. So metal, now one metal has given, suppose one electron away. It has given away. Okay, take it. So its respect increases, right? So metal is giving away, means its electron has reduced. Is the number of proton reduced? Like, is the metal donating it from the nucleus? No, it is donating it from the valence shell. Okay, take this electron. I have no problem. Right. Is this part okay? So, okay, to make you understand more clearly, forget everything I said. You know a basic thing, right? So you know that nucleus is present at the center. All the electrons are revolving in different shells. And in the nucleus, what is present? Protons and neutrons. Okay, so the number of protons is equal to the number of the electrons in normal condition for any normal metal. Now, one metal has lost one electron. It is losing electron. Okay, so the number of electron is reduced by 1, but the number of proton is constant. So the metal ion, neutron has no charge. Neutron is neutral. So that is why the metal will have more number of protons than number of electron. So the metal will have an overall positive charge. Okay. So positive charge is what? Now the what I will say, nucleus has become more positive. It is not has become more positive, but it is looking to us that it has become more positive. So it will just try to squeeze and attract the electrons. Power of positive energy increases. So they will attract the electron more towards themselves. And that is why they are squeezing it. And that is why their size is decreasing. Is this part clear? Why the metal ions are smaller than the atoms from which they are actually formed?
Ma'am,
Yeah.
is it means when we are removing an electron, is it means we are also removing the protons from the atom?
No. We are removing electron means we are removing only electron.
Yeah,
One
ma'am.
electron removed. Proton never gets removed. So if the proton is removing, you are not dealing with chemistry. You are dealing with physics. That happens in some atom bomb concept.
Okay.
Okay, there you are just breaking an entire thing.
Yeah, ma'am. That I
We
have
just
understood
play
that the
with
whole thing.
electrons. Yeah. So that will be taught to you by your physics teachers.
Yeah, ma'am.
Okay. Okay. So now is this part clear?
Yes, ma'am.
Yes, ma'am.
Okay. So let's stop here for today. Next class, we will be doing the rest of the parts. Okay. Hopefully you liked the session. Hopefully you understood everything more than you liking the session. I hope each and everyone has understood the concepts, right?
Yes, ma'am.
Okay then.
Ma'am.
Okay. So goodbye.
Yes, ma'am. Thank you, ma'am. Yes, students, now you can join the next session. Right? Join the next link that is from 8 to 9.